All right, ladies and gentlemen, thank you for joining me again tonight. Open Science Presentations. As always, my name is Ben Meekins. I'm a research assistant professor at the University of South Carolina. I started this project to provide a low-stress environment for people to share their scientific work, whether it's just to show off the work or to get practice for a presentation, or in the current age of coronavirus to maybe give a conference talk that they weren't able to give because the conference itself got canceled. Regardless, this project is meant for any scientist out there, anyone from high school up to a full tenured professor. Everybody likes to show off their work, and everybody can use practice. Even the most seasoned veterans, still need to do a run through every now and again. And I'd like to welcome everybody that's come in tonight and everybody that will show up throughout the talk. As always, if you're interested in giving a talk, please feel free to reach out to me. You can contact me on our Discord. The link for that's right below the stream. Or you can find me on Twitter at Meekins Lab, MEEKINSLAB, all one word. Or you can send me an email directly at meekins@sc.edu. That's MEEKINS@sc.edu. We would love to have anybody who wants to give their talk. It can be any topic, any length. The whole point is to basically have a practice run. Excuse me. So with that in mind, I will go ahead and get on with the talk tonight. If you do have a question that you want to ask, if you're in the stream chat tonight, if you're on Twitch, just type !Q, a space, and then your question, and it'll be collected by a Q&A bot. And at the end of the talk, we'll go through each of those questions, answer them, and then there could be some back and forth as well. If you're not able to type in the chat, make sure you click on the follow button. It's right below the stream, and that will allow you to chat immediately. I do keep follower-only mode on just so that bots and things like that can't come through and disrupt the chat. And so with that, I will go ahead and jump straight into the talk. So tonight I'm going to talk about co-electroless deposition of platinum metal bimetallic alloyed catalyst for methanol oxidation. This was some work done in collaboration with another group at the University of South Carolina, Dr. John Monier's group, and two graduate students, Greg Tate and Win Chong. I'll kind of get into it more in the talk itself. Greg and Win were responsible for the synthesis of the catalyst, and I did the characterization of the catalyst, methanol oxidation. And so I'll talk about each of those different parts, but I did want to point that out from the get-go. The first question, of course, is why are we even bothering to do this? And there's a couple of reasons. The first is that direct methanol fuel cells, otherwise known as DMFCs, have potential applications as portable power sources because they have both high power and energy densities. And we're already kind of set up to handle liquid fuels compared to hydrogen gas. Hydrogen gas, you either have to put it under extremely high pressures to liquefy it, or we need to find a different way to store it. Of course, if you're familiar with the field at all, metal hydrides are a current field of interest, but none as yet have really hit the thresholds in terms of combining both storage and ease of access to the hydrogen when you actually need it. And for that reason, even though liquid fuels are sort of not completely ideal, we are better equipped to transport and handle those liquid fuels, and so DMFCs are still of great interest. The primary issue, however, is platinum catalysts are sort of the gold standard. But platinum and carbon monoxide bond very strongly. And because of that, when you do methanol oxidation, one of the main reaction steps involves the formation of CO. And so that CO will bind to the platinum catalyst site, and once that happens, it doesn't really come off easily. And so as the reaction proceeds, the catalyst sites fill up, and so what you see is a drop off in the power density of the cell itself, because your active catalyst sites are being occupied for a long time by these CO molecules. And what decades of study have found is that if you have a secondary metal like ruthenium, you can actually get that secondary metal to help form OH species in a neighboring site to the CO that's bound to platinum. And those OH species actually help remove the bound CO. And so that increases your turnover by clearing out the catalyst sites. And of course, the optimal formation is a truly alloyed bimetallic particle. And what that means is that if you wanted to imagine a straight line, you would have platinum, ruthenium, platinum, ruthenium, platinum, ruthenium, all the way through. And so by doing that, you would always have a platinum and ruthenium atom, the two separate active sites, sitting next to each other as neighbors. And so that minimizes the amount of energy that's required for those two coordinating reactions to happen. Your turnover is maximized, and you get the highest possible activity out of your catalyst. And so what I've got down here at the bottom is just showing the anode reaction, which is the methanol oxidation in a DMFC, the cathode reaction, which is oxygen reduction to water, and then the overall reaction here, which is basically you take methanol, you add some oxygen or air, and you end up with just water and CO2. So it's a relatively easy reaction to deal with in terms of the products that are formed. Obviously, the issue of CO2 production is not great, but it's not hard to imagine this being paired with some kind of carbon capture system or even a carbon electrocatalytic reduction system. Those are two areas that are very big fields right now. There's a lot of time and energy and money being put into that, and it's likely that in the next decade or so we're going to have some actual economically viable solutions there. So again, this is kind of a more detailed breakdown of the methanol oxidation reaction pathway. Again, you start with methanol. It goes through multiple oxidation steps. But the big issue here is that the CO is sort of the primary one. And when that CO adsorbs onto platinum, your reaction pathway is broken until you can clear that off. And so that's the main issue that we're trying to deal with here. So let's talk about the way that we're going to actually make this catalyst. There's a couple of different ways that you can try and make bimetallic particles. You can just do a solution-based, metal salts in a liquid. You add a reducing agent. Both of the metals get reduced, generally in the same time, and you kind of hope that the two reduce together onto the same substrate. That works to an extent, but what happens is, in practice, is that you end up with a few bimetallic particles, but you also end up with monometallic particles spread all over as well. And what that means is that you're not really maximizing the efficiency of your reaction. And so you have a lot of wasted material, and the more wasted material you have, the more expensive the catalyst itself is going to be. Because to get to sort of your optimal catalyst loading, you're going to need to spend more money because you have a lot of extra product that you're going to use. And so the way that we've worked to get around this is through a technique developed by the Monnier group called electroless deposition. And the basic idea here is you start with a support and you have some base catalyst on this support. And so in this case, we used palladium nanoparticles on carbon. And I believe this is actually a commercial substrate. So it's 5% palladium on carbon. And the palladium itself is almost like a target for the reduction reaction. Although the palladium does not carry out the reaction, it acts as a selective substrate. So if you had just, say just carbon, you're not really going to control where everything deposits, and so you'll end up with larger particles and probably fewer of them. With this base catalyst, you can spread them out, and you can ensure that you end up with uniform distribution of these particles all across your catalyst substrate. And the general process here is you need to control three things. You need to control your pH, you need to control the temperature of the chemical bath, and you need to control the ratio between your stabilizing agent, your metal precursor, whatever it might be, and your reducing agent. The ratio of those determines how quickly the reduction happens, and so you kind of need to find that happy medium between a reduction that takes too long and a reduction that occurs so quickly that you end up with large nanoparticles that you can't control the size of very easily. If you control it very well, you can actually dictate very selectively the size of the nanoparticles that are formed by controlling the rate of the reaction. And one of the things that the Monnier group has done is they've actually demonstrated that they can use syringe pumps to basically continuously inject the reaction solutions into the chemical bath. And in doing so, they're able to dictate exactly how big the particles are going to be. It follows pretty intuitively that the more reactants that you add, the more metal is going to be reduced, and thus the bigger the particles are going to be. And so by controlling both the amount and the speed at which the reaction solutions are mixed together, they can actually very precisely control the rate of deposition and thus the size of the particles. More interestingly, they can do it with at least 3 different metals. So they've demonstrated at various points monometallic deposition, so just adding one metal to the substrate, bimetallic deposition, which I'm going to talk about tonight, and they've also demonstrated trimetallic deposition. So they can actually get particles that by all measurements are truly alloyed for anywhere from 1 to 3 metals. And in theory, as long as you have the syringe pumps and the right ratios, you could even go higher than that. You could do 4, 5, 6 metals all together at the same time. Whether there's any reason to actually do it, it's a whole nother story. But the capability is there. And so finally, by controlling all these, you get your selective deposition onto the base catalyst, and that's sort of the goal. So as I talked about, you've got your bulk co-reduction method here on the left. You might end up with a bimetallic particle, but your nearest neighbor is not really necessarily going to be a true bimetallic nature. So you will have some regions that are platinum rich, for instance, and some regions that are ruthenium rich. You might have some platinum and ruthenium neighbors, but it won't be an optimal mixing to where you're maximizing your active area. On the other hand, with the co-electroless deposition method, you're going to get atoms reducing in a very controlled manner. And by controlling the ratios and the environmental conditions, you're going to end up with more atoms with bimetallic neighbors than you would in a bulk reduction method. And so the advantage of electroless deposition has been demonstrated previously with some work that actually came out of our group in 2016. The Taylor Garrick showed with platinum and ruthenium, he compared a commercial ruthenium platinum catalyst, which was 50-50 ruthenium to platinum. That should be the optimal version, because you have for every platinum atom you have a ruthenium neighbor, and that should maximize your activity. And what he showed was that by doing this electroless deposition of depositing ruthenium onto a platinum carbon catalyst, he actually was able to get 3.5 times more activity than the commercial 1-to-1 ruthenium platinum. And what that demonstrates is that the more truly bimetallic your catalyst is, the more activity that you're going to get, which sort of reinforces that idea that you want to have platinum and ruthenium in this case as near neighbors to each other to maximize that catalytic turnover. It also shows that the electroless deposition allowed for very precise atomic ratio control, and so that lets you see that there's actually this sort of pyramid shape, or sorry, not pyramid shape, but sort of a peak that forms here with very precise ratio needed to actually achieve your maximum activity. If you're a little bit off, even 55%, 45%, you're going to see about 25% reduction in activity. And so, the exact ratio actually does matter a lot. So here's some older data as well from Bahari Takavoli. This was with platinum and copper, and what she actually found was that when the atomic, in this case, having a majority of copper compared to the platinum was actually where the peak activity occurred. So over here on the left, this is pure platinum. This is 20 weight percent platinum on carbon. It's about 146 amps per gram of platinum. And so what you can see is that as they go from majority platinum bimetallic to majority copper, you actually see that having a majority of copper with just a little bit of platinum gives you your maximum activity. You can almost double what your sort of baseline is with the platinum by itself. And so that sort of demonstrates the power of using this method. You can end up with these bimetallic particles, and you could find an optimal ratio between the two. What's the biggest thing here, though, is, of course, copper is significantly cheaper than platinum. So if you can reduce the amount of platinum that you're using and still increase the mass activity, you're going to have a more economically viable catalyst for your direct methanol fuel cell applications. And so when you bring down the cost of the capital cost of the DMFCs, now all of a sudden their utility is greatly increased. So the strategy here is to use this co-electroless deposition method to synthesize well-defined catalysts. We want to try and characterize both the bulk particles and the surface of the particles. The reason we need to do this is you don't want to assume, if you characterize the bulk of the particles, you're assuming that they're the same throughout the entire particle, and that's not necessarily true. It is possible to see segregation of atoms to the surface. Sometimes that's a desired thing, sometimes it's not, but it's important to know what's actually happening. And so then, based on that characterization, we can, we'll measure the methanol oxidation activity, and we want to try and correlate the physical characteristics to the activity that we observe, and try and figure out where the optimal ratios are for these different platinum metal bimetallic particles. And so here's an example procedure. So one of the metals that we used with platinum was nickel. And in this case, the reducing agent was dimethyl ammonium borane and with the platinum salt, and then ethylene diamine as a stabilizing agent. Basically, ethylene diamine will coordinate with the metal cation, and so it slows down the rate of deposition. And so what Wynn here did is she would actually pull aliquots during the course of the reaction, go and use inductively coupled plasma measurements to find out exactly how much of each of the materials was in the solution. And so what she could show is that based on the complete lack of platinum that could be detected in the solution itself, you know that the platinum must be deposited. And so what she can show is that the platinum deposits readily. And what you can't see here actually is the platinum 2+ being added is trending right along with this line. And so what it means effectively is that we've got 100% deposition. There's no wasted material of either the platinum or the nickel. And that's a really big thing. That really cuts down on the total amount of cost that you have, because you're not having to throw in extra metal just to make sure you get enough to deposit the way you want to. Rose up. There we go. Make sure I didn't miss one. Okay. Okay, there we go. Sorry, the pictures are kind of large. It takes a little time to transition. So here we have some XRD characterization. We have to be a little bit careful with the XRD characterization because the particles are pretty small. But what you can, the way we get around that is to basically deposit a large amount of the metals. And so you end up with large enough particles that you can do XRD characterization and be confident in the result. And so what we see here is when it's just the 5% palladium, we've got just the characteristic palladium peaks here and here. They're not very crystalline, so they're not really well defined. But then when you start adding platinum, you see the platinum peak build, and when you have when you add the nickel as well, what we don't see really is this formation of a pure nickel phase. And so what that tells us is that we're not forming monometallic nickel sites anywhere. We're actually getting a bimetallic metal deposited. So you can see there's a lack of nickel here, a lack of a nickel peak here. And so that lets us know that we're actually forming a bimetallic on this palladium particle. Similarly with cobalt, nowhere in here do you see a cobalt peak. Nowhere in here do you see a cobalt peak. Nowhere in here do you see a cobalt peak. So again, it tells us that we're forming this majority platinum, which is why we see a platinum peak. And then of course we had the palladium peak sort of in the background as well, but there's no cobalt peak. So there's no monometallic cobalt forming. So all the cobalt that's depositing is depositing with the platinum and forming some kind of a bimetallic alloy. And along the same lines, you can do you can use XPS to do a characterization as well. XPS it's a little bit weaker because we're using nanoparticles, and so, for instance, you can't really see that the nickel is there. You can kind of pick it out from the background, but it's not a very strong signal. But we can still extract mass and atomic concentrations. And the big thing that we see here is that the atomic concentration of the platinum and the nickel are roughly in the same ballpark. So we expect a 1-to-1, we get roughly a 1-to-1. We don't put a lot of stock in this at the moment just because the concentrations are so low. There is going to be some error involved in it, even with XPS. And so, we take it with a grain of salt, but at least what we don't see is, for instance, that the platinum is 5 atomic percent and the nickel is still down at 0.3. So we know that they're at least reasonably close to 1-to-1. Same thing here with the platinum and the cobalt. Again, the atomic concentrations are low. The cobalt signal is not fantastic, and so we're kind of, we're maybe reading a little bit too much into it at this point. But the same thing holds true here. The platinum is not significantly higher than the cobalt. We've tried using some chemisorption techniques here to figure out if they're basically we want to try and see if a certain ratio of the two metals will provide more active sites just based on, say, how the particle forms. And what both of these show is that there's really not any correlation between the ratio of the metals for either nickel or cobalt and the apparent active sites. And so that sort of throws out one of the potential explanations, which is basically, at this certain ratio, you have more active sites, therefore it obviously should be more active. That's not the case here. So we sort of eliminated that argument for ourselves. So the next thing to do is basically do the methanol activity measurements. And what this is going to do, we've done our characterization. We have a range of metal ratios for both platinum nickel and platinum cobalt. And now we just need to go ahead and measure them and see what we actually get. The way we do this is take the catalyst, put it into 1-to-1 water IPA liquid, sonicate it to suspend the particles, and then drop a sufficient amount such that we have at least 5 micrograms per square centimeter of active area. And then we use a Nafion solution. Nafion is just an ionomer solution that allows some particles to travel, or some molecules to travel through it. And it acts in this case as a binder. It's just there to hold the catalyst on. So we put a very, very thin layer on, and it's thin enough that it does not affect the activity significantly. And then finally, once that's dried, we cycle between minus 0.02 volts and 1.28 volts versus the reversible hydrogen electrode at 50 millivolts per second. We do that several times, typically 20 to 50 times. That is just to clean off the electrode and sort of hit a steady state very quickly. And then we cycle 3 times at 5 millivolts per second, and that's where we actually pull our current and peak current information from. The reason we do it 3 times is we want to make sure we want to be able to pull an average number of at least 3 trials. In a lot of cases, we have more than 3, but 3 is sort of the minimum that we're willing to work from. And so what we're watching for is if you see a major decline during those 3 runs, then you know that something's going on. And so you either need to redo it and make sure, see if you can get a steady state, or you need to pay attention to how it's decaying over time, because that tells you that your catalyst is not stable. So first I'm going to show the platinum cobalt data. I'll let the viewer guess which one is the best. It is very clearly platinum 2 cobalt. Everything else shows relatively little activity, whereas the platinum 2 cobalt is several times higher, anywhere from 5 to 10 times higher. This was repeated on 2 separate occasions, 2 different times on 2 different days. So it's not a fluke measurement. It is verified with 6 different curves. All averaged together, you get 390 amps per gram of platinum. So there's definitely a maximum case. And what we were trying to do here is sort of see if there was a peak. And so we went from, originally it was 1 to 1, 1 to 2, and 1 to 3. We saw this huge jump between, 1 to 1 was low, 1 to 2 was huge, 1 to 3 was low. So we wanted to check sort of a middle value here. So we did 1 to 2.5 and 1 to 1.5, and there's not really a peak here. You could argue maybe a little bit of 1 on this side, but more or less this 1 to 2 is the perfect composition. And you would have to get very, very fine, maybe 1 to 2.1 and 1 to 1.9 or something like that to start seeing a peak fall on either side. Similarly, for the platinum 3 nickel, or for nickel, platinum 3 nickel is the best. We kind of see the same thing. It is not as good as the cobalt, which is kind of interesting, but again, we have 1 to 1, 1 to 2, 1 to 3, and 1 to 3.2. The 1 to 3 is very clearly the biggest. Around 190 amps per gram of platinum. For reference, the cobalt was 390 amps per gram of platinum. The cobalt's better, but the nickel is also pretty good. And so what's interesting is that in this, for the cobalt, it was platinum 2 cobalt. Here we see platinum 3 nickel, and this coincides with the more well-known, quote-unquote, magic forms of catalysts. There's been a lot of work done with the oxygen reduction reaction where multiple groups have found that platinum 3 with some metal, a lot of times something like cobalt, is more active than just pure platinum. And I don't know that anybody's really got a good explanation for it at this point, aside from the secondary metal acting as some kind of assistance to improve turnover at the main catalyst site. But we did see that here with the nickel, but not with the cobalt, which was kind of interesting. One of them was sort of the magic form, one was not. But with all good things, there must be some bad. And in this case, what we found was that there were some pretty significant stability issues. The way this actually manifested initially was after, with the platinum 2 cobalt and the platinum 3 nickel, I had gone back to repeat them a third and maybe even 4th time just to make absolutely sure that the activity was true. But I used an ink that was about 2 weeks old. And when I ran the experiment, the activity was worse than just the platinum, the commercial platinum carbon catalyst. And of course, I immediately went back to my notebook and made sure that I had run multiple trials of these inks before, and in each case I had. In each case I had run two separate trials on two separate days, and both showed the same high activity. So the results were real. And so, of course, the question was, why all of a sudden do we see this massive decrease in activity? And as it turns out, when we did ICP analysis of the solutions, it turns out that there was a whole lot of cobalt and less, but still not an insignificant amount of nickel sitting in solution. And so what that means is that the catalyst was leaching out, or the cobalt and nickel were leaching out into this water IPA solution. And it turns out that it actually happens after just a few days. And so that's a big question that we need to answer, is what is causing this instability? Because if it's unstable, just sitting in an ink solution that's relatively mild, realistically, it's not going to last very long under actual operating conditions, most likely. And so that's something that we're still working on trying to figure out. It's really not clear at this point. It may be the case that it's a very high energy particle that forms, and because of that energetic strain needs to be relaxed in some way, and the way that it ultimately does this is by releasing some of the secondary metal that's involved. It may be that the reason for the high activity is that these secondary metals have some dangling bonds, which also cause them to be unstable. But that's something that we're working on. And so going forward, one of the big things that we need to do is some more characterization to try and understand this sort of magic composition. Whether it's the platinum 3 nickel or the platinum 2 cobalt, we need to figure out why those work the best. We also need to work to understand the cause of the instability. Like I said, you can have the best catalyst in the world, but if it's not stable, then it's not really going to do you much good. And finally, what we need to do is take these catalysts, once we understand them a little bit better, and actually put them in a direct methanol fuel cell, and confirm that the sort of small scale testing that we did translates into an actual closer to real life application, and see to check both the activity and the stability over time. Again, stability really matters, and so if it's not stable, we need to try and understand what's happening there, and see, is it temperature based, is it solution based, and is there anything that we can do to counteract it. And so finally, I need to acknowledge again Dr. John Monnier. He is an expert chemist. He did a lot of work in industry, has a number of patents to his name from that, but brings a very strong fundamental understanding to this. Greg Tate and Win Chong, they were the two graduate students in Dr. Monnier's group that did the synthesis of these catalysts, and provided the information on things like the ICP analysis, and some of the XRD analysis. And then I need to thank Dr. John Widener. He's a mentor of mine. He's no longer at the University of South Carolina. He took a position at the University of Cincinnati, but he's well suited for that. Still talk a lot. And of course, I need to thank the Hydrogen and Fuel Cell Center at the University of South Carolina. That was where I did most of my measurements, and so I use their equipment and facilities. And with that, I'm going to wrap up this talk, and I'd like to thank everybody for coming out. And at this time, I'd be happy to take any questions that anybody might have. All right, so there's no questions tonight. Fine. I'd like to thank everybody for coming out to listen. Just as another reminder, if you have an interest in giving a talk, please feel free to contact me. You can contact me here on Twitch, send me an email, meekins@sc.edu, or join our Discord. The link to that is right below the stream. Feel free to click on that, and it should just take you straight to it. Or you can follow me on Twitter and DM me there. Any of those is fine. I look forward to seeing you guys next week. We have a talk tentatively scheduled with Dr. Pralay Santra. He's an old colleague of mine who will undoubtedly have a wonderful talk. And then coming up on the 17th, We have a talk from Dr. Jim Siegler. He'll be talking about solar cells and some of the economic questions that surround them. And I believe we'll be talking about cadmium telluride cells in particular. It should be a very interesting talk, a nice combination of fundamental science as well as how it translates into applications. But I'd like to thank everybody for coming out tonight, and I hope to see you all next week. It'll be same time, 10:30 p.m. Eastern Standard Time. I will hope to see you all then. Thanks and have a good night.